All right, so our next presenter is Gabriel Casabona from Northwestern University. His field is theoretical astrophysics, and he did his practicum at Los Alamos National Laboratory.
Hello, good morning, everyone. I am currently a graduate student at Northwestern University, studying physics and doing research in astronomy. I'm part of Sierra, which is basically our center for exploration and research in astrophysics, and I work with Dr. Shane Larson. Throughout my time in graduate school, both PhD and master's, I've explored a bunch of different topics in astrophysics, from high energy explosions like super and kilonovas to some questions in relativity like black hole accretion disk. And so I'm going to talk about a few of these things, but first I need to clarify a few things and basically give you a quick summary of stellar evolution. So stars form from what we call a nebula, so basically just a giant cloud gas of hydrogen. And after that, once the gas gets massive enough, it begins to collapse in on itself, and it gets to a point that nuclear fusion starts. And at this point, we have a star. Now, the main component of a star's life depends on how massive it is in the beginning. So about 99% of stars, which are up to about 10 solar masses, will follow this top path up here, in which after the nuclear fuel, so this hydrogen, starts to burn off, it will swell up into a red giant, and then a lot of that mass will kind of just vanish out into space, leaving behind what's called a white dwarf. Now, a white dwarf is electron degenerate, okay? About 0.1% of stars, so between 10 and 30 masses, will follow this bottom path here, where after it gets massive enough, at some point, it'll collapse in on itself. And then from that, it's a high amount of energy from all different sorts of cool physics, which I'm sure somebody here will talk about in a poster this week, causes it to explode. And it's one of the most powerful explosions. We call these supernova. Now, there are various types, but one thing about these is that because of the explosion, it leaves behind a more exotic object. So between 10 and 30 solar masses will leave behind a neutron star. So this is neutron degenerate. And then the rest, so about 0.1, so over 30 solar masses, will leave behind a black hole. Now, the one thing about degenerate matter that you should know for this talk is that degenerate matter gets smaller the more massive it is. So a white dwarf that's 1 solar mass is roughly the size of the Earth. A neutron star of 1 solar mass is about the size of Manhattan. And a black hole is roughly like 7 kilometers in diameter. So the first thing that I began to look at were type 1a supernova, so the detonations of white dwarfs. And the basic scenario is that the white dwarf is in a binary system in which once it gets close enough to its companion, it begins to accrete matter from that companion onto the surface of the white dwarf. And as that material begins to accrete very violently, you begin to have very high turbulence. And the basic theory that we came up with was that once you have turbulence evolve long enough into which what we call the Kolmogorov scaling or cascade, where if you start off with a giant vortex for turbulence, you let it drive long enough till it gets smaller and smaller with smaller length and time scales. And once those time scales match the time scale of the fusion, in this case of carbon for white dwarfs, it will lead to a detonation. And so this plot here is looking at the ratio of these two time scales for nuclear burning, which is the way that astronomers say fusion, and turbulence as a function of temperature here. And for this dashed line up here is that point in which they match. These three different lines here are white dwarfs of different densities, so between 10 to the 4 and 6 grams per cubic centimeter. This would be the threshold at which you would find detonation. And so our theory proposes that you would need a white dwarf of 10 to the 6 as opposed to 10 to the 5 or 4. And so our first paper was looking at just that, looking at whether or not we can detonate carbon, and it worked. And so we progressed and now looked at helium. Now, white dwarfs have a very thin layer of helium around it. And we know from just basic physics that helium should be able to detonate a lot easier than carbon. And so this simulation here, done by one of my colleagues, shows that detonation starting and then propagating around the white dwarf, right? Now this needs to have a white dwarf companion, okay? And that'll be important in a second. So my research following up this was to see, can I detonate helium and carbon? And so we started running some simulations. We used Flash 4, which is a code that was made for problems like this, so high energy density physics. And we did it on a 3D grid, 512 cube cells. That's a very common scaling for any work that requires turbulence. With Helmholtz equation of state, 19 isotope network, and on a 100 kilometer box, so it's a localized simulation as opposed to a normal white dwarf, which would be on the order of like 5,000 kilometers. And I ran it with different abundances of carbon, helium, and oxygen, and different densities as well, like I showed before. And we ran this on Stampede 2, which has recently been deceased, I guess you could say. And we ran it, just for reference, the longest simulation I had to run was on 4,096 cores for about a week. And that was assuming that everything went perfectly, which it didn't, of course. And for some of the results, matching the plot that I showed you earlier, 10 to the 5 for pure helium did not detonate, which does match previous work. But when you started adding in other abundances, so here, helium being 0.25 means that 0.75 was an equal combination of carbon and oxygen. So we found detonations here, and then we also found detonations for all other ratios for 10 to the 6. So this was a good thing. Now, as far as nucleosynthesis post-detonation, I have a list of various elements here. Now, the first 5 of these is pretty normal. I didn't really care about this, but one thing that was important was this last one, titanium-44. The reason that I mentioned that having a binary white dwarf system was important is because when we've seen these long timescale observations of type 1As, we find the isotope for titanium-44, which has not been seen in other systems in the universe. And this is a snapshot of that detonation. So on the left, we're looking at a projection through one of the axes, and it's the nuclear burning energy. So the hot spot that eventually became the detonation is right here in the center. And on the right, you're looking at the exact same thing, except looking at the synthesis of carbon. One of the key results, surprising results, was that if I had pure helium, it led to the synthesis of carbon and then a detonation. And so this is the first time that work has been done where from first principles, we are able to synthesize seed carbon nuclei. So that's another one of the important results. And here is a graph or some plots showing that. So on the horizontal axis, we have time. And they're both showing the abundances of carbon and helium. The left is the mean value ratio across the entire box. And then on the right is the minimum abundance per cell. And so we see here, red dotted is helium, starting at 1, carbon 0. As time progresses and it gets hotter, the helium starts to burn, causing synthesis of carbon. And once it gets to a critical threshold of about 20% of the mass density, you then have a detonation of both. And you see that on both of these scales. So that's the main result in our paper. I boldly put this year, but I'm assuming, or I'm trying to publish this like yesterday. So for my next research, I look at gravitational wave science. And so basic thing about gravitational waves, a little bit of relativity for you non-physics folk, is that we treat space-time as one, and space-time is like the underlying fabric of the universe. And now if you have a pocket of space with no mass, we call that space-time flat, so it's kind of like this. And then if you have mass being introduced, the space-time starts to bend. And so if you have space and time, it starts to kind of do one of these things, right? And it's very pliable. Okay, and so when you have something intense going on, like black holes merging, a giant star blowing up, it sends a ripple through space-time in the form of what we call gravitational waves. Now, there's a laser interferometer called LIGO. We have 2 of them in the United States, and we have Virgo out in Italy, and then a few more around the world. These have been detecting gravitational waves now for a few years. And so the project that I work on is called LISA. And now LISA is going to be a space-based one. And so these lasers from LIGO are about 4 kilometers long. The lasers here will be on the scale of about the distance from the Earth to the Moon. And they will be able to detect gravitational waves at a lower frequency than what LIGO is here. So gravitational waves, we characterize it by strain, so kind of like how much space-time is being stretched out. That's on the vertical axis and as a function of that frequency. So you have LIGO over here on the right. Lower frequency would be LISA. Even lower frequency is nanograv. I don't know if you heard these announcements in the past couple of weeks, but nanograv uses even longer scales, and they use pulsars, so rapidly rotating neutron stars. And they have recently found a stochastic background from gravitational waves from what we believe are a bunch of supermassive black holes. And so one thing that I'm looking at is, again, with binary white dwarf systems, gravitational wave emission from it, but then also some resonance. And so the basic idea here is that if you have the gravitational wave being emitted, which is being emitted from the center of mass of whatever system that you're looking at, if that gravitational wave frequency matches the resonant frequency of the white dwarf, we expect that some of that energy will be transferred in. And so if you're looking at gravitational wave signals, we expect to see a drop-off in that signal before the coalescence begins to happen further, and then you should be seeing a further increase. So this is ongoing work now. We're doing it with COSMIC, which is a code made from our group that's a population synthesis code. So basically just trying to look at strictly populations within a galaxy of a variety of systems. It was designed for compact objects, but it can see other types of systems, and it's focused on binary systems as well. The next research is on collapsars. Sorry, I forgot that this had sound. Some of those stars that collapse down to a black hole can trap matter around it, which would lead to an accretion disk. And that accretion disk is plasma, so there's a magnetic field. The magnetic field gets stuck inside of the black hole. It threads through. And if that black hole is spinning, which all objects in space are spinning and moving, it'll cause like a whirlpool effect. So like if you ever been to a rodeo and you see them like swing the rope around and it like loops upwards, that's happening with the magnetic field, which then traps some of that material through it, making jets, okay? Now those jets are super high energy. You can see them like shoot out of a galaxy at what looks like superluminous speeds. And if those collapsars have a main sequence star companion, like our star, our sun, they could also emit gamma ray bursts, which are the highest form that a photon can take. And so I'm also using COSMIC to look at to see, A, is it possible, but also how many per galaxy should we expect, in what types of galaxies, and where to look. because that is important. Jets are very hard to detect because if they're not pointing directly at you, you won't see it. And then with neutron stars, I kind of talked about this before, but the first neutron-star merger was detected about 6 years ago, and it was the birth of what we call multi-messenger astronomy. So we detected it with gravitational waves, electromagnetic radiation emission, and neutrinos. And so 2 questions that remain is, how did it blow up? The neutron star has a very solid crust. It is the most dense material that we know of in the universe, and somehow it broke. And it's unclear how. And so the theory that I started working on when I was at LANL was to see if gravitational perturbations of the system, if it reaches the resonant frequency of that crust, can it break? And so this is ongoing research using a code called Spectre from the lab that I'm not too sure is published yet, so I couldn't really talk about much. But that's one question. And then the other question is, what object was left behind? Was it a more massive neutron star, or was it a black hole? And for that, we need an updated version of the fluid model for neutron stars. So using a fully general relativistic treatment for neutron stars using what's called the Israeli-Stewart model, which is just more complicated stuff, but that's currently what I'm doing now. And so that's a basic summary of what I'm working on. So in summary, the main computational portion was on the Type 1a supernova. I've kind of since transitioned into doing more theory, and so that's why the second half was more of a theoretical talk. But I'm using population synthesis codes to try and solve a variety of these problems, and ideally upgrading it to more advanced systems like potentially GPUs so that we can solve systems not just for one galaxy, but perhaps many galaxies at a time. And last but not least, I'd like to thank the APS Bridge program. That's the program that I went through after undergrad to go to grad school, where I went to UMass Dartmouth. My advisor at UMass D, which is with whom I work on supernova with, and my advisor Shane Larson, who introduced me to Lisa and all these cool relativity things. And at LANL, my advisor was Oleg Koropkin. That's the person that I was working on the neutron star crust problem with. And then Dr. Chung and Lloyd Ronning is who I've now collaborated with to work on the collapsar problem. And of course, all of you, the Krell staff, and especially my cohort, we talk a lot on Slack, and they've helped me solve a lot of problems with coding and life, all that good stuff. So thank you all for listening, and we can now go for questions.